All right, welcome again to the Real-Time Digital Signal Processing Laboratory class here at the University of Texas at Austin. So this is to go over the Homework 1 solutions. I've passed those out in hard copy, and please turn your homework in if you haven't already. There were 3 questions on this particular homework set, and we're going to discuss transfer functions and Fourier transforms. And there's sampling in there too. Again, a lot of review of signals and systems. We're going a little bit deeper than you may have seen in the prerequisite class. So let me kind of go through these solutions as we go. Okay, so I have the question embedded in the solution set. So the first question here is to look at 4 examples of discrete time filters that are very useful. And I'm going to hazard a guess it's going to be very useful in industry and in graduate school. They've been very useful to me. It's a very common, you'll see these commonly used in discrete time. And you will see that they have continuous time analog counterparts, and those are also commonly used in integrated circuit design for analog and in mixed signal design as well. All right, so let's start with the first one. So again, just for notation, x of n is our input, y of n is the output, little n is the discrete time index, unit less. So I've asked you for example, filters to give me the difference equation and the transfer function, and with the transfer function, the region of convergence. The region of convergence is useful for many things, so I'll ask you now, where have you found usefulness, and maybe it's new usefulness, that's fine, but what's useful about the region of convergence for the Z transform? What does that help us with? Go ahead. Helps us to know about stability, and so for in the Z domain case, what does that region of convergence have to include for bounded input, bounded output stability? The unit circle. So the region of convergence has to include the unit circle, and if it does, it's bivostable. That's use number 1. Use number 2, if it is bivostable, then we can convert the Z transform directly to a Fourier transform by substituting Z equals e to the j omega, right? So so for bivostability, again, bounded input, bounded output, stability. So I haven't asked you about the frequency response on this homework, but it is coming in homework 2, the next homework. So that I can find the frequency response as a function of discrete time frequency by taking the transfer function and substituting the unit circle, which is e to the j omega. Right, so as omega, which is real valued, takes values from 0 to 2 pi, I sweep out a unit circle, a circle of radius 1. And so you can see that because the magnitude here for e to the j omega is 1, just phase. This is the circle of radius 1. So if the region of convergence includes the unit circle of radius 1, it means that the region of convergence tells us what values of Z for which the Z transform converges and has meaning. So if the unit circle is in this region of convergence, it means I can do a mathematical substitution. It's valid. However, if the region of convergence does not include the unit circle, then I cannot do the substitution, and I would have to find the Fourier transform another way. We'll look up, you will use lookup, transform tables and so forth to do that when we need to. So that's number 2. What's the third use for the region of convergence? Is there a third use? There is a third use. I'm feeling like there's a third use. Does it help you find the poles? They're related. So the poles can help you find the region of convergence, and the region of convergence can tell you about some of the poles. So the region of convergence depends on the region of convergence. It will tell you about some subset of the poles.
It's outward, it's causal.
That's it. So if the region of convergence is the area of the complex Z-plane outside of the unit circle, then the inverse transform is causal. And if the region of convergence is inside a unit circle, the inverse is anti-causal. Anti-causal means time goes from 0 and goes backwards to minus infinity. That way. Yes. Yeah, the three things. Tells you whether or not, so if it's a Z transform and it's therefore you can, if it's a transfer function for a system, an LTI system, it tells you if it's bibostable. Use number one. The region of convergence must include the unit circle for bibostability. Use number two, if the system is bibostable or if the transform includes the unit circle in the region of convergence, then I can convert the Z transform to a frequency response. And the third option is to take the inverse Z transform. It tells me how to do that, whether I want the causal or anti-causal version. Now, for this class, will be causal. I mean, I will talk a couple of times about anti-causal processing, but for the most part, will be causal.
So when you say include the unit circle, does that mean that's to be greater than or equal to?
Yes, the unit circle must be included. It cannot be excluded. Right? Can't. So if I have a region of convergence. So consider this region of convergence. Circle here, but I don't include the points on the circle. And if this is the region of convergence, which is outside of this circle, that's the causal. That would be the causal inverse. Okay. And if the region of convergence includes the unit circle, then I know I'm bibostable, and I know that I can convert that Z transform to a frequency response.
Does it need to include the origin?
No. And we'll see that the origin gets excluded in certain cases. Anti-causal. So anti-causal means time we're going to run time backwards, and non-causal means that we're going to run time forward and backwards. Right? Non-causal is a little less clear what non-causal, because non-causal could mean anti-causal. I mean, it's not, or it could mean both causal and anti-causal. So there's causal, we run time forward. Anti-causal, we run time backwards. And non-causal, we may do both. Two-sided, basically.
So would that be where it is cut out, like where it includes which only two points?
That's right. You'll see a third option, which is a ring for and we'll get to this in lecture 5 slides. That's coming, that level of detail. We won't need the ring shape yet. That's coming. Okay. All right. So let's get on with the particular questions here. All right. So the first one was an averaging filter, and the averaging filter is really useful, and you can have as many coefficients as you want. And so this particular one is take the average of the current input value, which is x of n, and average that with the previous 4 input values. And this gives us the 5 coefficient case. So I have the current input, the previous input value 2 samples ago, 3 samples ago, and 4 samples ago. Right? And so strictly speaking, we're going to use a straight average, so we're not going to weight any one sample more than any other. So another way to think about this is I just take the sum of these 5 values, the previous input and the current input value and the 4 previous input values, and I take the average, which means I divide them by 5. It's not weighted. All the samples are equally important. And we can do this with any length. We can do it with 2. In slides, we did the 2 coefficient case. Just take the average of the current input and the previous input. And you can make this as long as you would like. Okay? And there's some interesting things about this particular averaging filter. First of all, it's really good at what? What is this? What's a good application for this filter? Getting rid of or smoothing noise, reducing the amount of noise. So it's going to take a running average. So if there's a little bit of uncertainty and jitter or additive noise among these 4 samples, that gets averaged out. Not necessarily removed, but averaged out, reduced. Okay. In terms of a frequency response, this particular filter is low-pass filter. And the cutoff frequency, the first null, so we do null to null bandwidth. The null to null bandwidth for this thing, we'll see this coming up later, so this is just a preview, but the null to null bandwidth is 2 pi over n where n is the number of coefficients. Okay, so for a 2-tap averaging filter, my first null is at pi. And for 3-tap, it's 2/3 pi and so forth. So it means that so what does this mean? It means the more coefficients I have, the more narrow my passband is. The smaller the range of frequencies that go through the filter, and the greater the number of frequencies that are attenuated. There's a hand.
Is this an ultimate what?
Bandwidth. Null-to-null bandwidth. Now, there's a implementation efficiency here is that we don't necessarily have to weight or divide by 5. Okay, so for simplicity, we might just take the sum of the current and previous 4 input samples and just change all these coefficients to 1. That's no longer, strictly speaking, an averaging filter, but it still has the same frequency response. It's still low pass. That doesn't change. The only thing that changes, if I multiply through by 5, it scales the magnitude response by 5, but the shape doesn't change. It's still low pass. And it's a lot faster for implementation. I've removed my divisions. All right, so let's talk about some initial conditions here. So when little n is 0, when I start producing outputs from this filter, and I assume I'm starting the inputs at also n equals 0, I have initial conditions. And I can see that just by putting in n equals 0, and I see that I have x of 0, x of minus 1, x of minus 2, x of minus 3, x of minus 4. These initial conditions correspond to delay blocks, if I were to draw the block diagram. And we need to find an initial value. And I haven't shown this yet. We'll do this next lecture. You can argue this from causality. You can argue this from linearity or time invariance. But the initial conditions here must be 0. So we just zero out the initial value in these memory locations. And that's kind of what we do naturally as programmers. But here it's what we really want to do to maintain these properties. Transfer function, I take the z transform of this. Wherever there's a delay by 1, I multiply by z to the minus 1. Delay by 2, multiply by z to the minus 2. So that corresponds to a delay. And so we have a polynomial in z. So again, this is more or less review on this particular question. Region of convergence, you asked earlier about 0. Well, because we have 1 over z squared, and so forth, we need to exclude z equals 0 to avoid the division by 0. That's the only exclusion here. It's the whole z-plane except the origin. The next one was the first-order derivative. And in circuit design, this is not as commonly used as an integrator, as a building block, but it does get used. Okay, and we're going to use it a lot in signal processing. We use this, and we'll see applications in later demos. We use this in image processing for edge detection and texture analysis. And we'll talk about why that is as we go here. All right, so the first order derivative, I pointed you to slide, I think, 3-20 on this one. We want to take so let's talk about a continuous time first. I want to take the derivative of the input signal. And it'd be great if I could observe the input signal for all time, from minus infinity to infinity, and then just take the derivative. That's hard to implement. So what we can do instead is look at a small neighborhood of the input and approximate the derivative by basically doing change of y over change of x. That's all this is. And you take the limit as the change in x, the change in the horizontal direction, goes to 0. That's our delta t. Now, the reason the limit definition is useful because then we can convert this to discrete time pretty cleanly by just sampling what we see here, the input-output relationship. And by sampling here, we mean replace little t with, all right, so sampling means I want to replace t with some integer multiple of the sampling time, usual stuff, uniformly spaced samples in the continuous time domain. So the smallest separation between samples in the continuous time domain is the sampling time t sub s. And we cannot make that 0, but we can make that small based on how we choose it, or choose the sampling rate. So higher sampling rate means a smaller sampling time. So what we can say is that we can now look at this in discrete time. So delta t then plays the role of our sampling time. That should be delta t. Right, so delta t is the sampling time. And so delta t becomes sampling time. And in terms of discrete time, if little t is replaced by n t sub s, it means that little t is our current sample at index n, and the value t minus delta t is what? What sample is that? N minus 1 is the previous input value. Right? And so delta t plays the role of the sampling time. So this becomes a very simple input-output relationship, very easy to compute, and it is implementing the first-order derivative. Now, there's some catches here that because I've sampled this approximation for the continuous time, first-order derivative is only valid up to what we can capture by sampling, which is half the sampling rate. So it's not, going to work for all frequencies, but we know that from the standard sampling theorem, the sampling rate's got to be greater than twice the maximum frequency. If you divide both sides by 2, it means the maximum frequency that we can capture through sampling is up to, but not including, half the sampling rate. Any frequencies above that get aliased down into the range that we actually are representing. We'll talk more about that later in the homework set. Okay, so this is our very simple filter, and in discrete time, we like to abstract away any notion of continuous time if we can. We like to be as general as possible, so that we can send the discrete time signal through any D to A conversion we want. So in practice, we like to get rid of dependencies on sampling time when we can. More generally, as I said earlier, we're going to play with the gain as we need to. And we'll just worry about it when we finally convert to continuous time through a digital to analog converter. So so we can actually ignore this gain term, and then finally, this is our very simple first-order difference. So all you have to do is take the difference between the current input value and the previous input value. There's no multiplication needed. One subtraction, one memory location to remember the previous input value. Pretty simple filter. Now this it's sort of a dual of the averaging filter. This filter is a high-pass filter. It captures high frequencies where the changes in the time domain are happening quickly. So for example, a discrete time signal that alternates 1 minus 1, 1 minus 1, 1 minus 1 has a lot of high frequency content in it. So if I have a discrete time signal that alternates between 1 and minus 1, that's as fast of an alternation as I can get in discrete time. And this frequency is what, minus 1 to the n, which is cosine what? Cosine what n is that? Yep. So minus 1 to the n is cosine pi n. That's the highest frequency possible that we can capture. Now, what I'm about to say should get you to think a little bit. What continuous time frequency would this correspond to? One half something, yes, 1/2. Well, that's how we convert continuous time frequency f naught to discrete time frequency. So what f naught is that? One half fs. So omega of pi corresponds to f naught equal to half fs. Now remember, this is a frequency that we don't always capture in sampling. We'll talk about that later in lecture 4 slides. Sometimes we actually do get this one. We'll talk about when that happens. It's interesting. So this is the highest frequency this is the highest discrete time frequency possible. Okay, so what does the high pass filter do? It passes through high frequencies and attenuates low frequencies. It does the dual of what the averaging filter does. All right, so Z transform here, very similar story. So take the Z transform of both sides, and I get, y of z is x of z minus z minus 1 x of z. And then I divide both sides by x of z, and I get the resulting transfer function. Again, pretty simple filter to implement, good high-pass filter. Now, why is it useful in image processing? It turns out that these fast alternations correspond to lines or edges in images and also texture. And I'll have demos of that later in lecture 5 slides. So this kind of filter, this kind of high-pass filter, is useful in detecting edges in texture in images. It's useful in many ways. So this basically pulls out the high-frequency content of an image, of a signal. And the averaging filter pulls out the low-frequency content in a signal. It kind of duels of each other. Region of convergence, same story. It's the whole z-plane except z equals 0. All right, next up, the first-order integrator. And I should say that the high-pass filter, the first-order difference is probably complementary is a better way to say that, not the dual. Dual isn't quite the right word, but complementary to the averaging filter. Now let's talk about the dual of the differentiator. That's why I had to make the distinction. So the third option was the first-order integrator, third filter I wanted you to look at. So in continuous time, this is a building block in integrated circuit design, electronics. And it's also very useful to us in discrete time. So here it is. So if I want to, basically integrator is simply integrating the input over the previous times that I've seen the input value. And there's an initial condition in here that needs to be 0 if this is an LTI filter. And the same was true with part B. There was one initial condition, which was the previous input value. That has to be 0 for LTI. So to make a discrete time version out of this, we can convert the integration to a summation. And again, we're making this causal. We're going to start at 0 at the origin. So that the discrete time version is, instead of integrating overall time from the time that we started, which is 0, we're going to sum overall time starting at the origin. And, it's the same story. However, the implementation here is kind of challenging because I now have to remember, if I implement it as I've written it, I have to remember all the previous inputs that I have seen. So as time goes to infinity, the amount of memory I need goes to infinity, not terribly efficient. We can be much more efficient by simply reusing the previous calculation. And so we can say, well, really the current output is the previous output, which is what we've seen so far, plus the current input value. And then for LTI, we have one initial condition, and that's the initial previous output value. We set that to be 0. Again, apply the z transform here, and we get a transfer function that you can write in terms of negative powers of z or positive powers of z. So where's the pole in this one? Where's the pole location? 1, z equals 1. The region of convergence has to be outside of that. We want to exclude 1. Why? Why do we want to exclude z equals 1? Why do we do that? You divide by 0. So z equals 1 is right out, so that's out of here. So we have to figure out, okay, so what do we do? So if we want the causal inverse, then again, we want the absolute value of z has to be greater than 1. Okay, so this is not bivostable. Okay. What's the impulse response of, I didn't ask this, what's the impulse response of this system? Unit step function. Okay, so how do you see that? So in the continuous time case, to get the impulse response, sorry, I have to go with 0 minus on this one or it doesn't work out. So if I integrate the direct delta, I get what function? I get the unit step. Right, that's the definition of the unit step. So the h of t, yes, I get h of t because that's the impulse response. That's the response of the system to the impulse. And this would be the step function. Discrete time? Go ahead, Danny.
I just wanted to know, what could be an example of some bounded input that would give an unbounded output?
Oh, very good question. So hold that thought, let me finish the discrete time. Actually, we can do it right here. So we'll do it right here in continuous time. If I put in a step function, the output is a step convolved with a step, which is a ramp. Right? So this, I have no idea what I just did.
You like dragged it down.
I dragged it down? Oh, well.
No, when you run the parentheses on the side, you actually drag that.
That's great. It's a new feature. Okay. You could say it's really bad handwriting. All right. All right, so again, the impulse response is the step. If I put another signal in, then it's the convolution of the input and the impulse response. And the impulse response is another step. Right, that's the ramp. Goes without bound. Discrete time. What's my impulse? Which one do I use? Remember what it's called? If you don't remember, it's called the discrete time impulse, and I guess it's safe. It's called the Kronecker. But what does it look like? At the origin, what's the amplitude? 1. And otherwise? 0. Okay, so it's an impulsive event. Now, if I take a running sum of this, the first input is 1, and every other input value is 0. So what's the output? 1. When n is greater than or equal to 0, which is which function? Unit step. So the impulse response in discrete time is the unit step. I can get this by just plugging in the step function, the impulse signal, and getting the response. I can do it in the time domain. Or what else can I do to get the impulse response? Think about it. Sometimes that works, okay? But a mathematical way to get the impulse response. I'm asking, how do I get that this is the impulse response in the time domain? How else can I do it? Inverse Z. So this this transfer function is the Z transform of the impulse response. So if I know the transfer function, I can do the inverse Z transform to get the impulse response. So the inverse Z transform of this transfer function is the step. Provided that the region of convergence sends me in the causal inverse direction. So if the absolute value of Z were less than 1, then this would be a U of minus n. I'd be going back the other way, the anti-causal. Okay, integrator is really useful in many ways. Keeping track of a measurement over time. This is also known as a running sum. So a way that you can compute an average is keep a sum of all the measurements until you finally need the average. So you have two memory locations. One keeps track of the running sum. One keeps track as a counter how many samples you've received. You need the average, just divide the two whenever you need it. Now, the integrator is the dual of the, what kind of filter is this? Well, the problem is it's not bivostable. So the problem we have is actually, it's a little bit more complicated here. If you exclude zero frequency or very low frequencies, you get a low-pass filter, a low-pass response. The unboundedness happens at zero frequency. So this is useful. So if you can use the running sum usually after you apply a removal of DC. So if you can remove the DC component, then you do the running sum, then you're safe in terms of stability. Okay, last part of this first problem was a damped bandpass resonator. Really useful in detecting frequency, a particular frequency buried in noise or some other signal. We use this quite often, and I mentioned it, I guess, in the homework set, but we did this for touchtone, the old touchtone telephone decoding, uses in where you're sending information by tones. This happens in Bluetooth and some other applications. This is extremely useful to lock onto one frequency of interest. So this has a difference equation. It looks a lot like the equation to generate a cosine. because it is. When R is 1, so when R equals 1, the impulse response is the cosine, one-sided cosine, when R is 1. So you've seen this already. We looked at this in slides. And I asked you more generally, let R be, for this problem, let R be between 0 and 1, but not including 0 or 1. Okay, but when R is 1, we get the cosine as the impulse response. This is a way to generate a cosine when R is 1. This is lab 2 for next week. If you look at this, we got 3 initial conditions. They need to be 0 for our system properties. Taking the z transform of both sides, a little bit of algebra to do here. But in the end, we get a second order transfer function because we have a second order difference equation. I have 2 pole locations and one. I could argue 2 zeros, but I certainly have, there's one that's pretty obvious here. If you multiply numerator and denominator by z squared, to put all the z terms into positive or non-negative powers, you'll see that there's 2 zeros, right? There'll be a 0 at 0. That's artificial, just from the algebra. So mathematically it's there, but it doesn't really affect us in the analysis. Okay, so to find the region of convergence, we want to go and find the pole locations. Here are the poles. So we just find the roots of the denominator for the poles. So quadratic formula, and we end up with pretty interesting stuff. The poles are in the z-plane. They lie on a circle of radius r. And the angles here are plus and minus omega naught. So I have a pole at plus omega naught and a pole location at minus omega naught. They are conjugate symmetric in location. And the angle with respect to the positive real axis is omega naught. And it's the same angle of the other, well, the negative, I suppose, but it's the same angular value here for the second pole location. So these are located, so poles are at r plus and minus. So r raised to so the phase is plus or minus omega naught, and the radius is r. Okay, again, for the causality, we want the region of convergence to be outside the pole of greatest radius. So the region of convergence is the part of the z-plane outside of the circle of radius r. Is this bifostable? But I said r is less than 1, so we're good. So yes, right on. So in this problem, r was between 0 and 1, but not including 0 or 1. Okay. I have no idea. Okay. That's problem 1. We'll revisit this in homework 2, do a little bit more analysis. These are 4 very useful filters in practice for audio, for speech, image, video, communication systems. Okay, the next one looks a lot like what happened on homework 0. I wanted to revisit this. So again, we're trying to compare the theoretical result from a 2-sided signal versus what we can observe in practice. We looked at that a little bit in homework 0. But now I want you to do it in a way where we don't need a continuous time Fourier transform to figure this out. And the reason for that is you like to be able to find some measure of bandwidth of any signal. You measure something in the lab, you don't have usually the formula for that signal over all time. You have data. You've captured measurements. So we want to find a way to capture measurements and figure out what the effective bandwidth is, or equivalent bandwidth. So for the first problem, the first part of problem 2, you know the continuous time Fourier transform exactly. You know the null-to-null bandwidth exactly. Then you can compare a simulation approach to finding that effective bandwidth, because you know what the answer is. So you know the ground truth. So I give you a rectangular pulse. It's of width 8 seconds. It goes from -4 to 4 in extent. I know this can't run out of ink, but somehow running out of sensitivity. Okay, so here's our pulse shape, amplitude 1. I know it's operator error, I know. Okay, so 8 seconds in duration, and the bandwidth, the null-to-null bandwidth in the frequency domain is 1 over this width. So it's 1/8. And you can see that by some experience from homework 0, but also just look at the Fourier transform. And if you plot it, the Fourier transform of the rectangular pulse is a sinc, and the first zero crossing in hertz will be, you see f tau here, so tau is the width, tau is 8. Okay, so this tells us the first zero crossing in the Fourier domain is going to be at 1 over 8. So if I look at the, see, I want to do the magnitude, I guess I'll do the magnitude. I get familiar sinc shape in this first zero crossing is 1 over 8, 1 over tau. So we know what the ground truth is, so we can go ahead and do this next by simulation to see what we get from doing that. And there's a few things to, as you may have experienced, a few surprises in doing this in simulation. So let's talk about some of those surprises. So first, the sampling theorem tells us that if we knew what Fmax was, or we could estimate what it is, then we have guidance on choosing the sampling rate. But in this problem, we're trying to find Fmax, so it's what we really want is we want to choose the sampling rate to figure out what Fmax is. Okay? So we can, as I wrote earlier, you can divide both sides of this inequality by 2 and see that the maximum frequency captured through sampling is up to, but not including generally, half the sampling rate. So we generally capture this range of frequencies through sampling. And frequencies outside this range will alias. So that's kind of observation 1. Observation 2 is building on the impulse train homework problem. My favorite problem in homework 0. And we'll use it a lot. Okay, so what did you see in that problem? Well, if we can model sampling as a product of the signal we want to sample and an impulse train. So I'm multiplying in the time domain, convolve in the Fourier domain, so I convolve the Fourier transform of the signal I'm sampling with the Fourier transform of the impulse train, which is another impulse train, and that those impulses are separated by the sampling rate. So the input-output relationship here in the Fourier domain is this. So what does this matter? Well, first of all, if I change the sampling rate, I'll scale the shape of the spectrum, which you would have experienced in talking to you in office hours. This was a common question. Yes, the shape won't change if there's not aliasing, but the scaling will change based on your sampling rate choice. Shape will stay the same, the scaling changes. Second, I get these replicas. So first of all, when n is 0, I get the true spectrum comes through from sampling. But then I also get an infinite number of replicas that are offset by an integer multiple of the sampling rate. And if we are obeying the sampling theorem, we won't have aliasing, at least for frequencies up to Fmax. Now in practice, we have frequencies, whatever Fmax we pick, if it's finite, in practice we have frequency content greater than that. So in practice, we'll always have aliasing. Bad news. We'll always have aliasing in practice. There's at least thermal noise up above whatever frequency. Anything above, at or above half the sampling rate, for the rates that we sample at, we're going to have thermal noise and other things. So in practice, we always have aliasing. If it bothers you a little bit, yeah, it bothers me too. But because the theory says we somehow we can get around this, but in practice, we can't. Sorry. And again, the other reason is finite observation. If we observe a signal for a finite amount of time, we get infinite bandwidth. So for those two reasons, noise and finite observation, we're going to have infinite bandwidth, even in theory. And in practice, it means we have content above half the sampling rate. So in this problem, what you can do is start with a really high sampling rate, because we know kind of what the bandwidth is. We kind of know what F max is for part A. So we know that anything above twice the null-to-null bandwidth will be something that's useful. So we can start. So instead of starting at 0.25 hertz, we can start at 1,000 hertz, or I think in the homework set I said 100 hertz. And you can then start at 100 hertz and then go to 10 hertz, 1 hertz, 0.1 hertz, in multiples of 10 until you see the aliasing. And the aliasing will be obvious because the shape will suddenly change. The spectral shape suddenly changes. There's something crazy, and you found aliasing that you can see. There's always aliasing, but not always affecting what you see or what you hear. But it is there's there. But eventually you get to a point where you see it. It's catastrophic, or it's really dramatic. Okay. And so you can eyeball this to finally find, just from looking at different sampling rates. Because the key is you want to make sure that you don't have significant aliasing when you're trying to find F max. So as long as you know your FS is high enough, then you can have some confidence in your estimate of F max. So here's the first problem we kind of know in closed form. It's a sink, and this point is always at half the sampling rate. So if you double the sampling rate, the shape will get smaller visually, but the actual frequency the zero crossings don't change when you inspect that. And this point over here is minus half Fs. All right. So for problem 2, it gets really hard to do this in closed form. So in problem 2, I have a sink pulse. It's really two-sided in theory, multiplied by a rectangular pulse to enforce the finite observation time over this range from minus 4 seconds to 4 seconds. Now, if I multiply in the time domain, I convolve in the Fourier domain. Convolving the Fourier transforms is not easy, right? Because the Fourier transform of the sink is what? A rectangular pulse. Fourier transform of a rectangular pulse is a sink. So now I'm convolving a rectangular pulse in a sink. Seems pretty hard to do that one. Seems really hard to do that one. And so this is a good case of, but can at least I look at the, so at least let's go back and look at the two-sided case. So the two-sided case is a sink pulse, and the Fourier transform is a rectangular pulse. So I know what that bandwidth is. Now I know, and that bandwidth is going to be, I guess 1 here. I'm trying to, seems like it should be 1 hertz. Then I know that when I do finite observation, yes, I'm going to get infinite bandwidth. But what really, the sink pulse, if I look at the convolution in the Fourier domain of the rectangular and the sink, I get a smearing or smoothing out or widening of the rectangular pulse in the Fourier domain. And I can use that to my advantage. I know that, right, so the sink, two-sided sink has a null-to-null bandwidth of 1 hertz. The second term has a main lobe width of 1 over actually should be 1/8 hertz. That's not right. It should be 1/8. Well, the lobe width is 1/4. The null-to-null bandwidth is, actually this is correct. So the lobe width, that is correct. The main lobe is 1/4 hertz. The null-to-null bandwidth is 1/8. So this is okay. So I know from experience with convolution, if I convolve two signals, I get wider. And so if I can approximate the signals here as finite width in the frequency domain, I have an effective bandwidth of 1 hertz from the sink, convolved with another signal with an effective bandwidth of 1/8 hertz, and a width, total width, kind of negative frequencies here of 1/4 hertz. So I know if I convolve the two, I won't get any wider than 1 hertz plus 1/8. All right, so again, I don't have to compute the Fourier transform, but I can kind of look at this and know, well, my effective bandwidth is probably 1.125 hertz, something like that. All right, so now let's go find it by simulation. So we go and sample. And so if we sample this, again, without any aliasing, this is our shape that we get. And again, we can start at a sampling of 100 hertz, then 10, then 1, until we see, and at 1 we should see aliasing. And we can then figure out by eyeballing what the effective bandwidth really is. So you could pick something down here around 1 if you wanted to. Depends on the threshold you choose. So you could defend here 0.6, 0.7, 1, 1.1. There's some flexibility in how you determine this. And the last problem is a one-sided, last part of problem 2 is a one-sided exponential, and that has a closed form Fourier transform, so now we know what the answer is. We know the ground truth explicitly. And, you know, this is a very common signal just from solving differential equations that show up in, you know, linear circuits, I suppose. And it shows up a lot for us, too, in discrete time. And so there's a Fourier transform pair out there, and so you know the exact Fourier content, and so you can find the bandwidth all kinds of ways, this way, analytically. And also, it tells you, what's kind of interesting about this is you can, whenever you see a decaying exponential like this, you can pull out the useful information right away in terms of frequency content and also time response. And that useful information is tau. So tau is a time constant. It tells you the delay through the filter in the time domain, if this were a filter. And 1 over tau tells you the bandwidth. Here tau is 1 in the problem. So that time delay is 1 second, and the effective frequency for that, or the bandwidth, is 1 hertz. And again, through simulation, we can find that approximate bandwidth. Okay, the last problem is sum and product of cosines. And really, this is an exercise in two things. One is the Fourier transform. If you add two signals together, take the Fourier transform, it's the sum of their Fourier transforms. So I have three sinusoids in part A, 10, 18, 33 hertz, and they're added together, so I get additive combinations. And there's a weighting, I guess, of each one, so the actual area under each one is slightly different due to the weights in front of them, right? So here's the weighting. So I take x1 plus half x2 plus 2 times x3. Okay, so that's the two-sided case, and if we do it in MATLAB, you're expecting some bandwidth, right? And you do. Again, because of finite observation, we don't get these spikes, we get some non-zero bandwidth. And the fall off is 1 over f. The last part of this is to multiply two sinusoids together, modulating one with the other. So I'm doing sinusoidal amplitude modulation. And so I end up with a sum and a difference of the two frequencies. I can get this through trig formulas. I can get this by writing cosines as exponentials. And I can do this through convolution in the Fourier domain, because I'm multiplying in the time domain. Any of the three methods will give you the same answer. So whichever one's easier for you is great. So any questions on this homework? Went through it pretty fast. All right, have a great weekend. See you on Monday. Solution sets are here if you didn't get one. There's mine.